Hello, this video briefly covers the sum of geometric series and its financial application, specifically in the calculation of annuities. We will begin with deriving the general formula for a geometric series. Then we will derive the general formula for calculating the summation of the present value of a series of periodic cash flows, which is an annuity. We will then apply these principles to the following financial example. How much money do we need to put into a financial account that earns 5% interest per year, compounded annually, so that we can withdraw $100 at the end of every year for 10 years? Suppose we are interested in finding the summation of this series of numbers: 2 plus 4 plus 8 plus 16 plus 32, and so on. This is a geometric series because each term is determined by multiplying or dividing by a constant, as opposed to an arithmetic series where each term is determined by adding or subtracting a constant. In our case, this constant is 2. In other words, each term is the double of the previous term. We can rewrite this as 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, and so on. Except let's end this now at 2 to the n. So we have n terms, and let's call this Sn, which is what we are interested in calculating. Now here's a technique that solves this in a pretty cool way. We know that each term is increasing by a factor of 2 in this series. Let's multiply this series by that factor of 2. We then get 2 times Sn on the left hand side, and every term on the right hand side will be multiplied by 2. So we get 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 4, and so on, until we get to 2 to the power of n plus 1. Notice how all the exponents have increased by 1. Then we subtract this series, 2 times Sn, from the original series, Sn. The left-hand side just becomes minus Sn. When we do this to the right-hand side, notice that all the middle terms cancel out, and we are just left with the first term in the original series and the last term in the second series. Multiplying by the negative, we get Sn to be 2, open brackets, 2 to the power of n minus 1, close brackets. Let's test this out for n equals 5 in our series. That is the summation of the first 5 terms. In other words, 2 plus 4 plus 8 plus 16 plus 32. Now we know this is equal to 62, but let's see what our formula gives us. 62. It works. More generally, suppose S is the summation of a series that looks like this: 1 plus r to the power of 1 plus r to the power of 2, and so on until r to the power of n minus 1. Note a couple of things here. The first term 1 could also be written as r to the power of 0. Also note that there are actually n terms in this series, not n minus 1. Multiplying this series by r and then subtracting it from the original series, we get s minus r times s on the left hand side. On the right hand side, once again, all the middle terms cancel out, and we are left with 1 minus r to the power of n. Factoring the left hand side by taking the s out and then dividing and solving for s, we get s is equal to 1 minus r to the power of n divided by 1 minus r, where r cannot be equal to 1, because then we would have a 0 in the denominator, and we cannot divide by 0. This is how the general formula is normally shown in textbooks. An annuity is a series of periodic cash flows. Now let's derive the general formula for the present value of an annuity. Suppose the annuity is a $1 cash flow at the end of every year for n years. Here's the timeline. Now letting v equal 1 over, open brackets, 1 plus I, close brackets, and discounting each cash flow, we get the following summation. S is equal to v plus v squared, and so on until v to the power of n. Note how the first cash flow is being discounted by a factor of v. The second cash flow is being discounted by a factor of v squared, and so on. Multiplying both sides by v, then subtracting from the original summation, and solving for s gives v times 1 minus v to the power of n, all divided by 1 minus v. Now substituting 1 over 1 plus I back into v, we get s is equal to 1 minus v to the power of n divided by I. This is the textbook formula for the present value of an annuity, paying $1 at the end of each year for n years, compounded annually at I% per year. Now let's apply this to our financial problem. Once again, we are interested in knowing how much money do we need in a bank account that earns 5% interest per year compounded annually, so that we can withdraw $100 at the end of every year for 10 years. It's very important to set up the timeline correctly, where each cash flow needs to be connected to a point in time. Here's the first $100 being withdrawn at the end of year 1. Here is the second $100 at the end of year 2, and so on, with the last withdrawal of $100 occurring at the end of year 10. The financial equivalent of the lump sum amount we need today is the summation of the present value of each cash flow. The first $100 will be discounted for 1 year, the second $100 will be discounted for 2 years, and so on. Once again, for ease of calculation, let V equal 1 over 1.05. So now our summation becomes 100 V to the power of 1 plus 100 V to the power of 2, and so on until 100 V to the power of 10. We can see that each term is being multiplied by V. Using the same technique from earlier, we multiply this series by V to get Vs, and subtract it from the original series. The left-hand side becomes S minus Vs. On the right-hand side, again, all the middle terms cancel out. We are left with 100V minus 100V to the power of 11. Factoring out the S on the left-hand side and the 100V on the right-hand side, and solving for S, we get 100V times, open brackets, 1 minus V to the power of 10, close brackets, all divided by 1 minus V. If you do the math, you will see that this simplifies to being 100 times, open bracket, 1 minus V to the power of 10, close bracket, divided by 0.05. This results in $772.17. Note V to the 10 is equal to, open brackets, 1 over 1.05, close brackets, which is V, and then raising that to the power of 10. This amount of $772.17 is the present value today of these 10 cash flows and is their financial lump sum equivalent. This is how much money is needed in the account today. Finally, let's understand how the present value of cash flows is related to the cash flows themselves. The blue bars here represent the cash flow of $100 every year for 10 years, totaling $1,000. This would have been the present value of these cash flows if the interest rate was 0%. The orange bars represent the present value of each respective cash flow. We can see that these bars are progressively reducing with time due to the time value of money. For example, a cash flow in the 10th year is worth less today than a cash flow in the first year. The total of all the orange bars represents the summation of the present value of all 10 cash flows. This totals $772.17. This is the present value of this annuity. And that includes this video on the summation of geometric series and a brief introduction to annuities.